So this is the first in a series of screencasts where I introduce some basics of hyperbolic geometry. The first screencast, my goal is simply to introduce the hyperbolic distance, what's called a Poincare metric. It comes from symmetries from complex analysis. That's the point of view I'll be taking. Let's look at it in a little more detail. First of all, we'll start with some very basic complex analysis, which is the uniformization. Well, what does the uniformization theorem says? Well, there are various statements, but I'll put a very simple one. So suppose omega contained in C is a domain and it's simply connected. Then omega equals 1 of, and here equals means equals in the complex analysis sense, biholomorphic. Well, it could be C itself, or it could be H, which is also D. Let me be specific here. H is the Z such that imaginary part of Z is greater than 0, the upper half plane, and this is the set of all Z such that mod Z squared is less than 1, which is the open unit disk. Okay, so this is the subset of the complex plane this way or this way. So these are the two possible pictures. This is of course all of the complex plane. And so the uniformization theorem tells you any simply connected domain is one of these. Of course, deeper versions of this tell you given any Riemann surface, its universal cover is one of these. So this is really a very useful way of understanding complex numbers. Now this is Euclidean in a sense that I'll make precise in a few minutes. And hyperbolic geometry is important because this is hyperbolic. Now there is a third possibility if you are allowing a little more general Riemann surfaces. It may be the Riemann sphere. Okay, that is not actually the spherical geometry in this point of view, which is why I'm not going to talk much about it. But what we want to do is introduce hyperbolic geometry in terms of being the natural geometry on the upper half plane of the unit disk, which, as I'm emphasizing, are sort of very natural complex analytic objects. Okay, so well, in what sense is C Euclidean? So C is Euclidean in the following sense, namely, what are complex analytic symmetries? So biholomorphic maps, well, let me call them F from C to C. This means holomorphic and invertible. Now invertible in any given sense is the same thing. You can ask for it to just have an inverse as a set theoretic map that is being bijective, and then the inverse is automatically holomorphic, in particular continuous. Okay, so it's holomorphic and invertible are biholomorphic maps. These are exactly Euclidean similarities. Well, with one little caveat, which is that they have to be orientation preserving. Okay, so as we see in high school geometry, Euclidean geometry, there are really two ways of viewing it. You can view things in terms of congruences, which is preserving distances, or similarities, which preserve angles, or a better way of looking at it is preserve angles and scale distances by a fixed amount. Okay, now any biholomorphic map F from CZ to Z is, so namely, any biholomorphic map must be of the form F of Z is AZ plus B. AZ is a scaling plus rotation because A is now a complex number. So complex multiplication is scaling plus rotation, and this is simply translation. So what we get are the different Euclidean symmetries, and A has to be non-zero. And any Euclidean similarity, provided it preserves orientation, is in fact of this form. So C is Euclidean in this sense, that is the natural geometry of C as a complex analytic domain is the Euclidean geometry, but with similarities rather than congruences. Okay, so your question here, okay, so question is what is the distance? Now there should be taken in quotes, distance preserved by the biholomorphic maps, that is the natural symmetries of H or D. Okay, we'll enter into these in some detail. For this we have to understand what are these biholomorphic maps. I'll just state the result and then understand whether there is a distance produced, preserved, and if so, is it unique, or to what extent is it unique. Okay, so this is not strictly speaking a meaningful sentence, but let me just, before entering into these detailed questions, just recall that upper half plane and the unit disk are equivalent by using the map from H to D, which will take Z to Z minus I by Z plus I. If this is not familiar, do it as an exercise. Show that the map from H to D, so I'll just say exercise here, show that this is actually a bijection between the upper half plane and the unit complex. You'll understand something by this. Some geometry, some complex analysis, well, complex numbers at any rate. Okay, so let's look at similarities or symmetries, complex analytic symmetries of H and D. Okay, and I'll be using whichever is convenient, freely passing between the two, but mostly it will be H. So what are the symmetries of Z? H. So some symmetries. It helps when we talk about the symmetries, of course, to have a picture in mind. Well, first of all, you have Z goes to Z plus a real number. These are just translations, but A has to be real, otherwise it won't preserve the upper half plane. But so long as it's real, you're just shifting, preserving the real line. A second class of symmetries is Z goes to Kz. Again, K is greater than 0, which implicitly in complex analysis means it's a real number. This means you're scaling things. So here's the origin. So Kz is just scaling things out like this. And the third symmetry, little less obvious, Z goes to minus 1 over Z. Okay, you have to put this minus 1, otherwise it will take the upper half plane to the lower half plane, the reciprocal. Okay, so these are all symmetries of the plane. And so composing these, well, if you look at compositions of these for various A's, K's, etc., you get exactly things of the form Z to AZ plus B by CZ plus D, with A, B, C, D real numbers. Okay, and the determinant AD minus BC, I shouldn't put mod here, simply AD minus BC. Okay, this itself is a fascinating story. What is the relation between fractional linear transformations and complex analysis? But I'll just not talk about that story. Assume that this part of the story is familiar to everybody. So we compose these, you get these, and of course here the theorem is that these are exactly the biholomorphic maps. Now we have a corresponding description on D, which is quite similar. I won't give that in detail because I really won't use it. I'll just use specific symmetries of D, where they are more visible than the corresponding one. So here are the symmetries, and recall our question. Question is there a distance that is preserved by these, and if so, what is it? Okay, so let me just say what kind of distance here. Obviously, I don't mean just Euclidean distance, but let's not look for arbitrary metric spaces. Okay, so in Euclidean distance can be given, of course, directly by a formula, but instead we can look at Euclidean length. Okay, so suppose gamma mapping, say 0, 1 to R squared is smooth. The length of gamma is the integral of from 0 to 1 of norm of gamma dot of S ds. Okay. Now I'll also have another quantity, energy, just to illustrate things. Is just E of gamma is integral 0 to 1 of norm of gamma dot s squared ds. Well, energy is nicer because it's quadratic. Yeah, everybody knows that quadratic things are nice. So I can write it as the inner product of this. Okay. So what we do is, this is the Euclidean formula. We look for a metric obtained from an inner product at each point. Okay, fine. So that is to say, we have an inner product at each point, and we want length of gamma to be the integral from 0 to 1 of norm gamma dot of s h. Okay, and maybe for now I'll put, for emphasis, this depends on the point gamma of s ds, and distance is shortest length, more generally infimum of length. Okay, but it will turn out to be the shortest length. So let me clarify here, rather than taking an arbitrary distance, what we are taking is what's called a Riemannian metric. That is, we assume that we have a measure of length at each point. Okay, that is an inner product at each point, which gives you a norm at each point, and we integrate that to measure lengths of paths, and the distance we are concerned with is going to be the minimum distance between 2 points, where we minimize overall paths. Okay, so this is the story so far. We want to know the length of gamma is integral of 0 to 1 of gamma dot of s. Yeah. So we want this kind of distance. Just some side remarks. Well, of course, we could look at completely general metrics, or we could look at metrics coming from norms and not require those norms to come from inner products. That's called a Finsler rather than Riemannian metric, which is also important in certain situations. But right now, let's say that our metric comes from the Euclidean, an inner product, which is different from the Euclidean one and is different at each point. Okay, so at each point is a distance. Okay, what can we say? Okay, so what can we say about this inner product h comma semicolon x? For now, I'll emphasize that it depends on the point x. Well, maybe I should say xy or something, or z, otherwise it will look at this thing. Well, what do we know? What can we say about this? Well, if we know nothing, we can't say anything. What we know is that this is preserved by symmetries of h. Okay, so the first fact here is proposition is the corresponding angles are the Euclidean angles. Okay, so the angles coming from hyperbolic metric are the same as the Euclidean angles. Recall that any inner product gives you angles. Why do we know this? So reason, there are symmetries fixing any point and inducing rotations, and here by rotations I mean Euclidean. Okay, I'm not going into details of this, but this is easier to see in the disk model. If we take our point to be the origin, well then obviously what happens is, if I look at z goes to alpha z, with mod alpha is 1, this is a biholomorphic map, and it's simply a rotation. Okay, and so in particular, given any vectors here, they are simply rotated at the origin. Okay, their length is not changed, they're simply rotated, and so the induced map on the tangent space is just a Euclidean rotation, and this has to be a symmetry. Okay, from this one can conclude that rotations at any given point are symmetries, Euclidean rotation of the given inner product, and this can only happen if the angles are the same. Okay, so that's the relatively easy to see proposition. Now at any given other point to say the same thing is not so easy, but it uses the fact. Okay, so in general you use holomorphic maps preserve angles. This is a basic property of complex analysis. So putting these together, okay, with a leap of faith, what we can see is that the new metric differs from the Euclidean one by not very much, namely the angles are the same. Okay, so let me now use the term conformal metrics. Okay, so as this inner product at whatever point z has the same angles as our usual inner product, which I'll put an E to emphasize is Euclidean, we have, well, now if two inner products give you the same angle, simple linear algebra tells you that this is some function phi of xy, okay, where z is x plus iy times the Euclidean angle. So from trying to find this complicated object which is an inner product at each point, we are reduced to finding a function. Okay, now what do we have by further symmetries? First of all, z goes to z plus a in R symmetry implies phi of xy is in fact only a function of y. Okay, so because we have horizontal translations, it tells you that if I take a pair of vectors here and look at their inner product, or I translate them and take the pair of vectors here and look at their inner products, these two inner products should be the same. Okay, but in one case is the Euclidean inner product multiplied by phi at this point, and in the other case phi at this other point, and since they're equal, so the scaling factor should be independent of x. It's only a function of y. And then secondly, z goes to kz being a symmetry, okay, implies that c of y is some constant by y squared. Okay, let me justify this, because this is let's take any point and let's look at a vector here. Okay, now kz, we'll take it to another point above and a much bigger vector, much bigger in the Euclidean sense, if k is large of course, namely this has length, so if this has length 1, this has length k, Euclidean length k, but the hyperbolic length should be equal. Okay, that can only happen if we scale, okay, that is if we scale the hyperbolic norm by a factor of y, 1 over y, sorry, over the Euclidean norm, to cancel the fact that things have expanded. Okay, so the y squared comes for the inner product. By the way, I put a 1 over y, in fact, so in general I would have root c here, but I can, without loss of generality, I could take it to be 1. Well, it's a loss of generality but nothing else. Okay, so that is to say we have a metric which is 1 over y times this, will the scaling invariant forces this. Okay, so this is really the only, so this has forced, so thus we have a formula. Hyperbolic norm is 1 over y. Okay, I think this deserves a new page. So thus hyperbolic norm is 1 over y times Euclidean norm. Okay, so this is the big formula we have deduced. Let me just recall the steps that were involved in deducing this formula. We just looked for a metric of this form. Okay, so I should say we should verify that this works. Okay, and what should we verify? For z goes to 1 over z as well, minus 1 over z as well. Okay, so this is the exercise to end this little screencast. So what we wanted to do was we wanted to find out if the symmetries of the upper half plane or the unit disk looked at as complex analytic objects correspond to something geometric. Okay, namely, are they isometries, or is there some distance which is preserved by these symmetries? Okay, well, we tried to work out what that distance was, and a scaling factor is arbitrary, because if any distance is preserved, some scale of that is arbitrary. But otherwise we just assumed this distances of this Riemannian form, that firstly the angles are the same as the Euclidean angles, and next that the scaling factor which works is 1 over y. I mean that this is the only scaling factor that can work. Well, but in deducing this, we also ended up checking that it was preserved by right translations and also by the scaling maps. What we didn't check was this circle inversion map, that this circle inversion map preserves the result, but one can verify this by a simple calculation, and that tells you that the symmetries of the upper half plane are exactly the maps that preserve this. Okay, so with that I will